Hello students, today we will discuss on spread spectrum multiple access techniques. We have learnt already the different wireless communication characteristics, and we have also learnt about the diversity. We have learned about the receiver techniques, and we have little bit understanding that in a wireless communication domain, in a spread spectrum supported system, so for example a code division multiple access based systems, we will have multiple users in a network where simultaneously they will try to access and they will try to send their data to the intended users, and that is the general nature of any wireless communication networks. Today we will try to see when these multiple users try to access the medium, wireless medium, basically to transmit their independent data, and how will it happen and what are the different techniques and the mechanisms are there to support the successful communication between two users over such a network. We understand that in a spread spectrum communication system, multiple users can access the network, can transmit their data at the same time at the same frequency, and they will be segregated by each other from each other by the use of unique key or unique spread spectrum sequence. Actually, the communication that happens in a network, if you try to see, it may be a point to point, I mean one user targeting another user, or it can be a multiple users targeting sending data to a point. A good example of multiple point targeting to a user is the multiple users trying to send their data to the base station from your handset. You are trying to transmit to the base station, like you. Multiple such users can try to send their data from the mobile handset to the base station. That is a multi-point to a point communication. When point to point communication goes on, then it may be a single user directly communicating to another user, or it may happen that one base station is communicating with another base station directly. Whatever it is, if it is a point to point communication, then the situation is, we sometimes call it a station to station communication also. So, this point to point communication, the major problem is when you are sending your data to your intended user, how in a receiver you will detect and decode your own intended signal when all others are also transmitting their radio signals, and they are giving severe amount of interference to your signal. So, because we understand all the users can simultaneously transmit at the same time and the same frequency, so interference is obvious to happen, and the question is how you will detect your own signal, intended signal, in presence of the other users who are supposed to be the interference to you. Multi-point to point, in that situation your target signal, your main problem is sitting in the base station in the receiver. How will you detect each and every user signal separately? How will you detect, how will you decode the several spread spectrum signals separately? So, the problem definition is different. In a point to point communication, interference is going to play a role to detect your own signal, and where you do not have a load to sometimes detecting the other interfering signals, you may or you may not also. But in the base station receivers, when multi point to point communication is going on, sitting in a base station receiver, your problem statement is to detect and decode each and every user signals in the presence of the other interfering signals. So, we have given an example in the figure 1 and figure 2 as an example of your point to point and multi point to point receivers. See, this figure is basically for point to point. We have shown that in figure 1 it is multiple data sources. S stands for the sources. Here is a destination. So, multiple signals, once they are coming, local data sources, they can be multiplexed, and this is a node. Inside a node is the multiplexing going on, and hence in the transmitter output you are getting one-to-one communication, because destination is fundamentally getting multiplexed signal from multiple source. It is a point-to-point channel. So in the receiver, so from transmitter to receiver, after receiving in the receiver, what's happening is receiver is demultiplexing the data to separate out the different source signals, and it can target different destination also. So this is a typical, the channel itself is a point-to-point channel. So there is no concept of multiple transmitters that are interfering your reception. It's not like that. So this is a point-to-point channel, and because of this it is basically based on the multiplexing and demultiplexing of the signals to separate out the multiple sources and multiple destinations. So this is one kind of the way of handling the multiple access over a point-to-point channel. Next is the multi-point to point communication. Let us see how will it happen. So the corresponding multi-point to point, it is, we call sometimes it is a distributed multiple access mechanism, where your channel will be multiple point channel or multiple access channel, where what you will find is there are specially separated data sources, and each of them are having their independent transmitters. All of them will be transmitting, and hence the receiver is bound to get the signal not only from the intended transmitter but also from the other transmitters. And this is a central destination. If I am targeting, it may be a base station, and these are all the mobile handsets or the mobile stations that you are carrying. And this is a very typical wireless communication scenario that we face in our day-to-day life. It may happen in opposite way also. Suppose if it is a base station to multiple mobile stations, the communication is going on. Then from the same transmitter, single base station transmitter, it will be broadcasted. So once it is broadcasted, the signal will be received via to the different receiver via different kind channels. So the channel of the receiver 1 and receiver 2 and receiver 3, they are not exactly same, and that's a downlink channel that we call. The channel like this, when mobile station to the base station communication is going on, we will call it an uplink channel, as we have discussed earlier also. And this is the downlink channel when the transmission will be going on from the base station to the mobile stations. So multiple access here also is received. The channel is basically the distributed multiple access, we call it. That's why the mechanism is. And this is a distributed multiple access channel, and this is a distributed broadcast channel. You are broadcasting the same data to multiple receivers. So these are the basically two different types of the access that we face in a wireless communication network, and that we will also be facing when the space spectrum communication is going on over that network. So now it is obvious that if two users are using the same channel, same wireless environment over the same frequency at the same time, so two packets released from such two users, there is every provision that they will be colliding with each other. So but this collisions needs to be resolved, because otherwise for both the users the packet will be won't be able to detect it in the intended receiver. And one possible solution of that, or I should say the one of the possible solutions of this problem, is something like this. You have a channel, wireless channel, it has a maximum capacity, and what you can do it, the total radio channel capacity is to use you can actually divide the available whole bandwidth of the channel, which is equivalent to the proportional to the capacity, and we can utilize the whole bandwidth of the channel. We can divide it by multiple subbands, and we can have a frequency division multiple access. So the users who will be allotted in the first band and the users who will be allotted in the band number 2 or band number 3, they can never actually collide. The packets of these three users can never be colliding with each other. So like that you can actually divide the available bandwidth over several sub bandwidths, and the sub bands we call them with smaller bandwidths, and allocate the each smaller bandwidths to each and every user, to multiple users who are intended to send their data over the wireless communication channel, and thus you can avoid the interference from user 1 to user 2 to user 3 to user n. But remember one thing, actually whenever you are dividing the whole available channel into the smaller subbands, so basically you are not doing good over the anti-jamming capacity of this per spectrum communication, which fundamentally comes from the fact that you are using a very wide bandwidth where the narrow band jamming signal will be rejected once actually you are receiving, you are spreading your transmitter signal over the wide bandwidth compared to the narrower interference. So, if I am reducing and restricting the bandwidth of my spreading, definitely if I am dividing the total available bandwidth by smaller sub bands, so the bandwidth I will get for spreading over for each and every user who are allocated in this sub band, that will be much less compared to the total bandwidth available, and hence the its capacity to avoid, or its capability to avoid the anti-jam activities, and capacity to prove the anti-jam activity for the receiver, that will be definitely reduced. So so that's why actually we don't prefer the frequency division multiple access as a preferable or natural choice for the space spectrum communication systems, because in space spectrum communication our fundamental motto of design is a secure communication design, where by default you will get by the means of signal processing you will get a protection against the jamming activities over the environment. So if we are not preferring the frequency division multiple access technique as a preferable solution for the space spectrum communication, so let us go a little bit forward, and the next option itself is, instead of dividing the available frequency over the bands, let us assign actually each and every user radio with a spread spectrum carrier. I mean, you divide the available capacity over the carriers, spread spectrum carriers, and this is specified by some pseudo random. These carriers or the spread spectrum carriers are the pseudo random which is specified by the pseudo random sequences, and hence this is a key, not only a key assigned to each and every user, it is also assigning the spread spectrum carrier to each and every user, who all will be spreading their signal using their independent key or pseudo random sequences, and they can actually parallelly start their transmission, because all those keys will be designed in an orthogonal fashion. So we the whole mechanism, this way we call it a spread spectrum multiple access mechanism. Remember that the key should have some very specific fundamental properties, and what are those properties we will see in the next slide. To avoid actually the multiple user interference over the network, we should be very much aware of the fact this spread spectrum signals with these different keys, the keys should be designed in such a way that all the keys should be statistically independent to each other, and they should be orthogonal also in the statistical sense. For example, actually they should be completely uncorrelated random processes. Each and every key should be a completely uncorrelated random processes. It means actually their expectation, if you do the time cross correlation and that you take the expectation of this time cross correlation values, it should give you perfect 0. And these orthogonal signals, in fact, that can be, we have understood actually a lot of the ways of generating such orthogonal signals in the last few modules, and these are the signals who will be utilized now for the spreading your original signal, and they can be having of different lengths based on the data rate requirement, giving you the flexibility of varying the data rates inside the network. For example, see actually this orthogonal signals, when we generate using same kind of the it can be generated by some kind of the waveforms as spread spectrum signals, But remember that we always actually define their spread signals and their spreading waveforms by terms of some chip sequences, and as a orthogonal signals and the relation of the chip sequences. Fundamentally, after spreading the signal with these chip sequences, remember that you are finally coming up with, not in the bit domain, you are finally coming up with the chip domain, and the property of the spread spectrum, or the property of the spread signal, will be governed by the property of these orthogonal chip sequences. And these are some known facts to us already. We have heard about the frequency hopping MFXK systems and frequency hopping MFXK waveforms. Their hopping sequences we can choose such that during a chip time or a hop time, it may be equal to hop time also, the no two signals should hop over the same hop duration. So if that can be ensured, then definitely you can provide the protection against the multiple axis interference. Suppose you have designed two signals in such a way that the hopping pattern for the first signals, it is something different from the hopping sequence of the next one, and such a way that the two within a chip sequence or within a hopping duration, two such hopped signals are never coinciding or never falling with each other, never be overlapping with each other, then definitely you can avoid the interference from each other, such two users. And this phenomena will hold good as long as the chip sequences are time synchronized among all the transmitted radios over the network, which is very hard really to maintain in a practical scenario. And if we relax little bit the chip synchronization requirements, we can use some chip sequence generation in such a way that they won't yield perfectly zero cross correlation values, but they will generate a very low cross correlation. Then also the system design is possible. And in such a sequence, for example, we have heard about the gold sequence priori, and Bend sequence is also another sequence who can give us a very low cross correlation values. So for FHMFSK waveforms, the hopping sequences, they yield on at least very low time cross correlation values, and hence it is actually at least we can assure that if such sequences are given to two different users, they won't provide zero interference to each other, but they will maintain a very low interference profile over each other. So signals with this same form as the spread spectrum signals designed to have a very low time cross correlation, they are basically used to they are mostly utilized in the practical system designs, and we do not prefer to use and we really do not get the flexibility to use perfectly having the perfect statistical property over the multiple codes. So when we continue the design with a condition that the codes that are getting used in the spread spectrum systems, they are maintaining a low cross correlation property rather than assuring a zero cross correlation, time cross correlation, we then call the system as a code division multiple axis, not the SSMA. So the distinguishing factor between your CDMA and the SSMA is something like this. In the CDMA system, you can expect that the codes that are getting used, they will have a low cross correlation profile, whereas in your SSMA, you will assume that the chip sequences are completely statistically independent with each other, and they will be regarded as a random process, independent, identically distributed, but completely statistically independent random processes. So this is very much, I should say, this is very ideal situation, and this is close to the practical situation. And so the CDMA signals that we will be coming here, the signals that we will be utilizing here, they are defined as those will having a low time cross correlation values, as I have already mentioned. And if you see that the CDMA signals, if the CDMA signals are having very long period, they will be asymptotically coming close to the SSMA signals, because in that case the low, cross correlation values will be so low that it can be approximated as almost 0, which is the case of the SSMA. So, we have learnt about FDMA, then we came to SSMA and CDMA. Now, the time is to go for discuss about the other kind of the multiple access techniques, which is called the time division multiple access or the TDMA. What we do in the TDMA is that the total capacity of the channel, actually it is over the whole available bandwidth of the channel is allotted to all the users. They can use the same frequency also, but the time of their operation is not same. So, what I can do is now if this is my time axis, what I will do is over the time axis I will allot the user number 1 some time being, then I will allow the user 2 to access my channel at the next time being, and like that the time scheduling will be associated with each and every user, where all of them users given actually the time, within that time he has the flexibility to use the full bandwidth of the channel and the same frequency. So, this is the time division multiple access where the disjoint slots are exploited and they are assigned to different radio communicating channels. They are actually given to different users, and remember, unlike the frequency division multiple access systems, here the time difference between two users actually ensure that you won't get any interference from each other. So, just as a single frequency and frequency division multiple access system, it can be used in the TDMA also. But remember one thing, in the frequency division multiple access, the center frequencies of the FD subband used to be different. Here you are not doing that, and here similar to the SSMA and the CDMA, they are both close to the SSMA and CDMA. But you can nicely club actually the CDMA with the TDMA, or you can also club with the FDMA with TDMA, or you can also club with the CDMA with FDMA. So, whatever be the way, actually depending upon the application scenarios and the kind of the data rate demand and the quality of service, the multiple such techniques are actually exploited in practice to get actually the prevention against the interference experienced over a network by the users. So, using this because of this disjoint slots, already we have discussed that the TDMA format and the TDMA itself can ensure you the interference protection. And another important thing to remember here, so as we are having the different time slots, so the pseudo-random sequences that we are using for the users who are operating in this time slots, the same set of the pseudo-random sequences I can allot to other set of the users in some other slot, provided the data transmission of those users who are using this set of the pseudo-random sequences, their data transmission is over. So, once the data transmission is over it, as these pseudo-random times are orthogonal to each other, they are disjoint. So, sequence can be repeated over the multiple time slots like this. So, the number of the keys you need now to operate over the channel, they are not that number of the sequence, number of the cores required to operate are really not as high as the CDMA. So, it is a nice actually process and a nice situation actually, but definitely the TDMA involves a high delay and the waiting period to get the access of the channel. CDMA is not providing you any delay. Each and everybody can have an access of the channel almost instantaneously, but remember, you have to have a huge set of the orthogonal keys or orthogonal codes to segregate the users and their data. And this is really a very big question, because getting a huge number of the orthogonal codes simultaneously to densify the network mainly is a very big question. It's hard to get So such a big number of the orthogonal code sets for separating the users. The third point was our frequency division multiple access. It has its own limitation. We saw that you cannot get that much protection, that much anti-jamming capability, as you are reducing the transmission bandwidth, and which is only a part of the total available bandwidth. So these are the four different kind of the techniques, including SSMA. There are four different kind of the techniques, and they are having their own kind of the pros and cons, and based on the service application, based on the data rate requirement and quality of the service, we choose any one of them or a combination of them in the practice to design the network. Another point to make here is, if you are using a TDMA system, and we will discuss here actually with respect to that point. Okay, suppose that essentially if we have a match filter architecture in the receiver that have the separated correlators, parallel correlators that can detect the peak of the different signals with their relative time delays are happening, and if this delay is more than the chip delay TC of with respect to each other, then what we can do is that all these independent correlation peaks uniquely the time varying match filter it can detect. So what we can do is, if I understand that this is the peak of the signal 1, correlated output 1, so I can follow actually regularly the peak of corresponding to the 1 to actually capture the signal from definite user. Similarly, to get the signal from the user 2, I should always follow the peaks corresponding to the 2 for a regular interval, and same for the 3. So basically, if the time division multiple access, if the two chips are if the two signals are separated out, or they are delayed from each other more than a chip duration, so they can be treated as a separate signal, and there is basically no interference from one signal to the next signal always. So if you are having a chip alignment, if you are having some alignment within a chip duration only, then this kind of the interference, the problem of the interference will come into picture, with two users will be transmitting using the same frequency, same code, and your same frequency, same code, and same time. And moreover, we are having some interleaver also in the circuit, so it will also take care of the fact that you get actually a pretty good resilience against your interference. So the different random access schemes are there in practice, and Aloha is a very popular one out of that, and it doesn't restrict. This Aloha random scheme is such that it has no restriction over the number of the radios and when a radio can transmit kind of. And in this Aloha scheme, the radio transmits at any time, and it has a message whenever it has a message, and it can listen also the acknowledgement. So it can transmit whenever it is having a message, and it keep on listening whether some acknowledgement is sent from the intended receiving radio, by the intended receiving radio. If no acknowledgement is there, so it will keep on retransmitting his own signal, so in a random fashion. Then actually a lot of collisions may happen, because of everybody will try to send their message in a random fashion. In order to improve the performance, people came up with the slotted Aloha scheme, and in the slotted Aloha scheme, wherever this random transmission is going on, this random transmission is restricted always by the some fixed time slots, and this implies that all radios must maintain that fixed time reference, and then you can keep on randomly transmitting your signal and keep on listening for getting the acknowledgement from the intended receiver. But after that, actually the carrier sense multiple access these days, which is used mostly in these days, they are the most popular and advanced version of this Aloha and the slotted Aloha. They give a much better performance in terms of accessing the wireless channel. In carrier sense multiple access everywhere, which tells that every receiver or every nodes who is having some data to transmit, he first listens the channel and try to understand whether some transmission is going on or not in the same frequency, and he waits till actually the channel gets free. Once he senses that there is no transmission at that frequency is going on, at that moment only he starts releasing his own packet, and he tries to establish a link over the channel. So that's the carrier sense multiple access. Each and every user obeys this typical rule of listening before talk. It is a listen before talk also. The more complicated and the more complex random access techniques that can be actually also allowed apart from the CSMA, and that are the utilization of the channel. But remember, actually to better utilization means you have to have a better channel state information or side information also to get the information, a prior information or access the condition of the channel. And that extra information that we use required to give this information about the condition of the channel is not bandwidth efficient communication, I should say. So that is a call, actually how much complicated calls you wish to go ahead with. And now this collision CSMA schemes, actually space spectrum signals are generally very difficult to detect. So the CSMA scheme is not that much preferred for the space spectrum. Slotted aloha requires some time synchronization among different radios that may be done by the GPS, but that also actually cannot be 100% guaranteed. So it is also difficult to achieve. So though actually that's why sometimes actually we prefer to go ahead with a slotted aloha basically, and or some advanced version of the CSMA for the space spectrum communication. And signals and the notations of this non-overlapping time slots and all, that's not very much useful, because we have understood that if actually they are one chip duration away from each other, the collision can be actually avoided. And so they don't collide the same spectrum carriers if they are having the same intervals, also if the time delays are more than the chip duration. And with the pure aloha random process also, the two spectrum radio signals can cause a collision at receiving radio, but only if both of them using the same key. So you can flat away use aloha, and if you are 100% confirmed that the keys are perfectly orthogonal from each other. And so otherwise, so that's why actually basically in a jamming environment or in a multi-user environment, we can treat the other users signal from the intended signal to be behaving as a just like a independent jamming interference. The space spectrum multiple access now with this direct sequence BPSK waveforms, if we try to see. And here when a transmitter and the receiver are using the direct sequence BPSK waveforms, and you are receiving the signal with an additive white Gaussian noise, and all other interference, multiple users are on, so all other interferences here can be modeled as also as an additive Gaussian, having a Gaussian distribution. And the pseudo random sequences are statistically independent to combat the interfering signal, or reduce the effect of the interference. And for many CDMA systems, so the signals are not perfectly independent. This Gaussian approximation also can be justified if the large number of the users are present in a network. And we also assume for this analysis that the radios in the network where the different keys have the statistically independent pseudo-random sequences, and these sequences are modeled as a sequence of independent equiprobable binary random variables. And let us consider that we are considering with a low autocorrelation values of those sequences, and it's not a SSMA system, hence it is a CDMA, as where actually it is a CDMA system it will be. Then typically for this, though practically most of the situations will be following the CDMA system, for this situation, for this analysis, we will consider that the condition is following the SSMA, or mean the keys are perfectly orthogonal to each other for the ease of the analysis only. And so the for known fixed times, the network key is issued by all the radios, and otherwise each radio uses its own unique key for receiving the DSBPS or for receiving the DSBPSK transmission, and they can transmit also either using the same key or by the different key that is already provided by the network. The point to point communication system, if it is going on, where the interference or the jamming signals are coming due to the other users present in the network, and suppose we are having the capital L other number of the users on. So the total jamming power, the JL, that will be varying, actually is a summation of the power actually released by the user 1 to user L. So at the receiver in the question, when the intended signal has a power of the S, we can have the effective bit energy to the jammer noise given by this expression. This is a known expression for us. This bit energy to the jamming noise power is nothing but the gain divided by J by S, where this PG is equal to the processing gain, and which will be giving by the number of the chips present within one bit, and J is nothing but the summation of the all the other users power. So summation of all the JLs. Remember, this analysis is considering that there is a continuous jammer of power J, and the additional gains because of the coding, channel coding, and then I mean the coded or uncoded spectrum communications we have not considered. That gain will be additive to this processing gain coming into picture. And we know that if gamma is bit energy to noise ratio that achieves as a desired bit error rate probability, then the total interference, so this JL should be always less than equal to this n by gamma. It can be lower bounded by, actually it can be lower bounded by the n gamma multiplied by the signal transmitted S. This if the analysis whatever we have done for this point to point SSMA analysis, that actually is for CDMA analysis and the SSMA analysis. So for both DSB PSK systems will be having approximately the same way, and difference mainly actually will be in the way that you are doing the averaging. And generally when the number of the CDMA signals are really very large, we understand that it goes close to the performance of an SSMA signal, and so in that situation there will be an averaging going on directly over the fading channels. If I consider there is a Rayleigh fading channels, this ratio of the bit energy to the noise power will be now given by the average jamming power to the average signal power, because you are now considering the fading channels and the multipath the powers that are received over the multiple paths from each and every user. So now you are taking a mean and or a mean value over that. So that's not the instantaneous power or the instantaneous values over each path that you are dealing with. Hence actually the average values of the signal power and average value of the noise power is coming into, or interference power is coming into picture in the expression. So this is about the fundamentals of the different multiple access techniques, and a very little discussion about how the error probability or the received signal to noise ratio will or signal to interference ratio rather to say will behave in a multiple access environment in a spectrum communications.